मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, dear students, this is 20th lecture in the series of mechanics of metal forming. Two part, the very basic concept of metal forming, including deformation, basic deformation theory, was discussed in part A. Part B was purely on the mechanics part, where the stress at a point, strain at a point, tensorial notations, and then yield criteria and all those things we discussed. Now we are going to start with the third part, C, which will deal with the modeling and simulation technique in metal forming processes. So purely whatever the techniques, modeling, mechanics has been evolved so far, those can now be used for modeling different, including the constitutive equations and all those things. So there are many equations. And if you recall, previously we derived basic equations which is required for solution of elastic plastic deformations. These equations, along with, if you apply the proper boundaries, if you remember, so we had equations of equilibrium, we did compatibility equations, yield conditions, stress-strain relations we derived, and strain displacement relations we derived, incompressibility conditions for plastic strains, and boundary conditions in stresses or displacement of, or the mix of these we would see. The stress-strain relation in plasticity are non-linear, and yield condition in case of the one mices is also non-linear. Therefore, it is not easy to solve these equations without some approximations and simplification of material properties. So, in case of metal forming, the difficulties are increased because of four main reasons. Number one, in many of the forming problems, the boundary conditions are not known, not very clearly known. That is very important to be known. Secondly, as the plastic deformation proceeds, the material properties go on changing due to strain hardening that we have already seen. And third one, at high rate of plastic deformation, when the temperature of deforming body increases because of the heavy deformation, which also changes the material properties. High temperature not only lower the flow stress, but also initiate stress relieving and recrystallization, which results in softening of the material as well. The strain hardening and softening may take place simultaneously, in fact, during a hot working process. The resultant properties, therefore, of the metal depend upon the temperature and the rate at which the process is carried out, that we have already seen. Fourthly, which is very important, phase change may also take place during plastic deformation, which can also change the strength property of the metal body. the whole workpiece. The nature of interfacial friction between tool and the metals seldom is not very known exactly. And therefore it introduces another approximation. So these 4 points are very important, and having an exact solution, which means taking into account all these above 4 points mentioned are factors, is enormously very difficult to follow altogether. So approximations are bound to be there in almost all simulation process or modeling process. In bulk metal forming processes, the plastic deformations are very large, as we have seen, as compared to the elastic deformation, and therefore elastic deformation may be neglected and the material may be taken as rigid plastic or rigid work hardening material that we had been doing so far. This approximation is common to most of the solution of metal forming problems, except those in which the elastic and plastic strengths are comparable, such as in seat building case. In case of work hardening material, most of the researcher, if you look back, have taken isotropic work hardening, because taking into account the anisotropy produced during the process makes the solution much very difficult. So in order to be able to solve the metal forming problem, drastic approximations are made, both on the material properties as well as on the governing equation side. The different methods so far that has evolved for solution for different problems, one can note down like the methods has been slab method, slip line method, upper bound technique, lower bound technique, numerical techniques, and finite element method. So far, now it is very popular. The first 3 methods, that is slab method, slip line method, and upper bound method, almost these 3 methods have been abundantly used. The popularity of finite element method is steadily increasing, and in today's because the FEM is very versatile, and availability of availability of powerful computers and high-speed processing machines at cheaper rate, now it has become possible to use FEM approximations very easily and at lower cost. In slab method, the problem is basically simplified by approximating the equilibrium equations. Basically, we solve equilibrium equations. The application of slab method is discussed. We would be discussing later at after few lectures, and however, very few solutions have been obtained so far using lower bound technique, because usually civil engineering applications are more concerned with lower bound. Slip line and upper bound method have been used abundantly and form the main topic of discussion, particularly in these lectures subsequently that would take place. So to start with, we would be looking the slip line theory, because it has been, however, the slip line theory concerned with 2D plane cases only. 3D is possible, but it is very difficult, and because the finite element technique has come up, so now it is almost discarded, the slip line theory, even though as a theory, because it started with many things, so we should look into. So in slip line, we would see the plane strain slip line, where the alpha and beta lines, stress equations, velocity equations, Henke's first and second theorem, velocity discontinuities, stress discontinuities, stress boundary conditions, free surface, frictionless interface, interface with sliding friction, interface with sticking friction. These we would be looking into under slip line theory. Then because slip line can also be drawn graphically, so construction of slip line fields and related hodograph we would see. Application of slip line, then one can apply the theory, the equations that are used for many field techniques like plane strain compression with frictionless platens, indentation of semi-infinite mass by a flat frictionless punch. We can also see the indentation of semi-infinite mass by frictionless wedge-shaped punch. Plane strain compression with perfectly rough plate and drying of rectangular strip with frictionless tapered dies we would be going through. So let us start with the basic theory of slip line. The slip lines, in fact, directions are in fact direction of maximum shear stress in the body which undergo plastic deformation. For the plane strain deformation, the equilibrium equation, if you remember, and along with yield equations, yield criteria, either it is one Mises or Tresca, for plane strain case are solvable for three variables, if you recall. So three variables like sigma xx, sigma yy, and sigma z xy, where it is in under the plane strain condition. The partial differential equation along with yield condition in plane strain are in fact hyperbolic partial differential equations. Their solution admits discontinuities. So directions of maximum shears are the characteristic direction of these equations. Therefore, slip may take place along the planes of maximum shear. In fact, the slip takes place on the entire maximum shear stress surface. However, in most of the cases, only we considered across the cross section of the body. So we see lines of maximum shear stress, which is called as shear lines or slip lines. Let us suppose we take the directions of maximum shear as coordinate directions and transform the equations which is given here in second and third along these directions. So if you look at this figure number 1, where the curvilinear element of a slip line field is shown. So if we see here, so one can see that along these directions, these equations, that is your equilibrium equations and conserving yield criteria equations, get converted into algebraic equation. It has to be get converted. This is in tuned with the general properties of hyperbolic partial differential equation, and we would be looking into all these things here. So if we consider the plane strain, so the stresses, that is sigma xx, sigma yy, and tau xy, that is the shear stress, are in fact function of x and y only, and therefore the plastic strain, that is xx, yy, and the corresponding strain rate, plastic strain rate, all are equal to 0. That means the plastic strain rate epsilon xx, epsilon yy, and epsilon yz, epsilon strain rate, plastic strain rate, xy, yz, and so this is all equal to 0. So according to plastic stress strain relation, if you recall, the plastic strain rate is what? It is it can be taken as which is equal to, and it is proportional to derivative part of the stress, because we take the z direction in plane strain condition, that is the plastic strain rate in z direction is 0. So one can find out that sigma zz prime becomes is equal to twice sigma zz minus sigma xx minus sigma yy divided by 3, and that is in fact derivative part is 0. So this what it guides that the slip line technique, in fact it is a graphical approach, and it depends on the formation of the plastic flow pattern in deforming a material. The plastic flow generally occurs predominantly by slip or planes of closely packed atoms, and in the direction of the lines of atoms, if you recall, which lie closest to the direction of maximum shear stress. In a real material, however, it is reasonable to assume that there will be sufficient number of favorably oriented planes for the slip direction to coincide with the direction of maximum shear stress. In an ideal material, that is a structureless, homogeneous and isotropic material, the slip line will always occur precisely in the direction of the maximum shear stress. Thus, once the direction is known, the direction of plastic flow in an ideal material can be established. In a deforming material, the plane of maximum shear stress form an orthogonal curvilinear network, which is one can see here in figure number 1. The orthogonal network of characteristics of the lines maximum shear stress have come to be known as the slip line, therefore. In a rigid perfectly plastic material, the element is subjected to yield shear stress, that is the maximum shear stress K, and a mean normal stress, that is hydrostatic stress or hydrostatic pressure P. If you recall, the direction of principal stress, say sigma 1 and sigma 2, are at 45 degrees to the slip line. The third principal stress, that is sigma 3, act normal to the plane of the figure 1 if you see. The major feature of the slip line field theory concerns the manner in which solutions are arrived at. Instead of the usual way of deriving the solution, here the solution is first proposed or thought of, and then it is known to be kinematically admissible, and that is that it satisfies all the boundary conditions. Kinematically admissible means that the proposed deformation pattern is compatible with the known flow of the material, that is the null direction. Obviously, the solution proposed will not be unique, and and other criteria may have to be considered to obtain the best possible solution. So, if we consider the plane strain, the general problem of three-dimensional deformation using the slip line field technique is, however, very difficult. It is still interactable, but it is possible to analyze plane strain problem. 3D problem, it is very difficult to solve with slip line. So consider the case where flow or deformation is parallel to the given plane, say XY plane, in a system of three mutually perpendicular planes. In other words, flow is independent of the z axis, therefore. So the basic plastic strain increment in this case can be written as d epsilon x, which is can be equal to deva ux by deva x. D epsilon y is equal to deva uy by deva y, and d epsilon z, because in z direction it is 0, so d epsilon z would be equal to deva uz by deva z, and this in fact is 0, and therefore it can be further extended as d for the shear component, like c d epsilon xy is equal to half of the deva ux by deva y plus deva uy by deva x, and deva epsilon y d epsilon yz becomes half of deva uy by deva z plus deva ux by deva y. This in fact is 0, and similarly d epsilon zx is equal to half of deva uz by deva x plus deva ux by deva z, and this is also 0. This has been shown here in equation number 1, these three set of equations, where ux and uy and uz's are the displacement, and d epsilon x, d epsilon yz and d epsilon zx are the 0, since uz is 0, so all the component that comes with 0 in the strain increment is 0. So if you use the one Mises-Yield criteria and its associated flow rule, one can write down this set of equation number 2. So that means d epsilon x becomes 2/3 of d lambda, and then multiplied by sigma x minus half of sigma y plus sigma z, and similarly epsilon d epsilon y becomes 2/3 d lambda multiplied by sigma y minus half of sigma x plus sigma z, and subsequently, because the z component is 0, so this comes out to be 0, and therefore one can write down that sigma z, that is becomes half of sigma x plus sigma y, and the mean hydrostatic stress, which we represented earlier as P, and that also was represented at sigma m, is can be obtained as 1/3 of sigma x sigma y plus sigma z, and that is because sigma z is 0, and therefore it becomes half of sigma x plus sigma y, and that is equal to sigma z, because the epsilon yz, epsilon zx are 0, and sigma z is a principal stress. So if you now apply the incompressibility condition, that means sigma x would be equal to minus sigma epsilon, that is strain in x direction, would be equal to minus of the strain in y direction. The state of stress on a plane which is inclined at an angle, say psi, from the direction of maximum shear stress can be represented on a Mohr circle diagram. If you recall, we plotted the stresses when on two Mohr circle construction, we for the 2D case as well as 3D case we considered. So now it can be plotted. Let us see it in figure number 2. Here the principal stress, that is sigma 1 and sigma 2, are known as compressive, and therefore we can use the von Mises criteria, and that gives sigma xx minus sigma yy square plus sigma yy minus sigma z square plus sigma z minus sigma x square plus 6 times as the summation of sigma xy square plus sigma yz square plus sigma zx square, and that was equal to twice sigma square, and that was also equal to 6 times of the shear stress square. And under plane strain condition, the same equation, von Mises equation, it reduces to this form, where the component, the fourth component on the left side, which was it will come as rest of the will be that means sigma x minus sigma y square plus 1/4 of the sigma y minus sigma x square plus 1/4 of the sigma y minus sigma z square plus 6 of shear stress xy square, and that would be simply 6k square, or 1/4 sigma x minus sigma y whole square plus the second term becomes the sigma xy square, and that is equal to k square. So if you see here this figure number 2, under the plane strain deformation case, so all these things have been plotted. So sigma 1, sigma 2 and sigma 3, and then one can see here this is what the angle to psi. This is along the x direct stress, and along the vertical direction this shear stress has been shown. So if you see the equation number 6, this can also be obtained directly from the Mohr circle, as shown here in equation number 2. So if one required to find it out directly from the Mohr circle, it can be for the von Mises, it can be simply written as sigma 1 minus sigma 2, which is equal to twice k, because p equals sigma z and that equals sigma 3, that is half of the sigma 1 minus sigma 3, and it is equal to k. So from this Mohr circle, particularly this particular case, the Mohr circle for the von Mises and Tresca becomes same under plane strain deformation. So with this background, as I told, these lines are inclined at 45 degree, and therefore in between the lines there are 90 degree difference. So these lines are called as alpha and beta lines. So the two direction of maximum shear stress, where with alpha and beta of the slip lines are therefore mutually identified and are mutually inclined 90 degree at each point, and that is what we call it as alpha and beta lines. The usual convention for identifying the alpha and beta line is that when alpha and beta lines form a right-handed coordinate system axis, then the direction of algebraically greatest principal stress, say for an example it is sigma 1, say, which is shown here in equation 3, lies in the first and the third quadrants. The anti-clockwise rotation which is psi of the alpha line from the direction x, it can be taken as positive therefore. So if you see here in figure number 3, where the curvilinear element has been shown here, so here is the x and y, and then one can see this is what's the direction of algebraically greatest principal stress. So this is what's the, and that is along sigma 1 1. So you can see here the hydrostatic pressure and the shear stress. These are mutually, which is the perpendicular along one, and this is what we call it as, this line as the alpha line and this line as the beta line. So this is tangent to the beta line at O, and here it is tangent to the alpha line at O, both. So this is what with respect to this figure number 3, now we can write down the stress equations. So let us neglect the body and inertia forces. The stress equilibrium equations can be written, that is deva sigma ij divided by deva xi, and that is equal to 0. So for plane deformation, that is the plane strain deformation in xy, if you, with respect to figure number 3, the plane can be written as if you see here, that is deva sigma x by sigma x plus deva sigma xy by deva y is 0, and the second equation is deva sigma y by deva y plus deva sigma xy by deva x, that is 0, and that is what is shown here in equation number 8. Because sigma yz and sigma zx is 0, so more circle for the plane strain, which if you recall the equation number in figure 2 gives sigma x, sigma y and sigma xy from the Mohr circle. So that becomes sigma x is equal to minus p minus k sine 2 psi, and sigma y as minus p plus k sine 2 psi, and sigma xy is k cos 2 psi. So this is what is shown here, and if we differentiate these equations with respect to, let's say the x is differentiated with respect to x, and subsequently that gives minus dp by dx, deva p by deva x, minus 2k cos psi and deva psi by deva x, minus sine 2 psi deva k by deva x. And similarly we can also write down differentiation with respect to y, and this results into this, it is written here in equation number 10, and the shear part, that is the deva sigma xy divided by deva x, becomes minus 2k sine 2 psi and deva psi by deva x plus cos 2 psi deva k by deva x. And if we substitute these equations 10 into equation 8, one can again get as minus deva p by deva x minus twice k cos 2 psi deva psi by deva x minus sine 2 psi deva k by deva x minus twice k sine 2 psi deva psi by deva y plus cos 2 psi deva k by deva y, and that this summation is equal to 0. And the same thing again written for the y component, and that is what these two equations is shown here in equation number 11. So if x and y axis are chosen to coincide with the alpha and beta line, for example, that is, we can then take that size becomes 0, and in that case these equation number 11, set of two equation which is shown in 11, it can be written and simplified way. That means minus deva p by deva x minus twice k deva psi by deva x plus deva k by deva y is equal to 0. This is what about along the alpha line, and minus deva p by deva y plus twice k deva psi by deva y plus deva k by deva x is equal to 0, and that is what happens along the beta line. So if we integrate this equation 12, so that can be simply found that minus p minus twice k psi plus integral deva k by deva y dx, and that is constant which is along alpha line, and similarly minus p plus twice k psi plus integral deva k by deva x dy is again a constant along the beta line. So for a rigid perfectly plastic material where the equation, this equation 13 can be very easily written as that p plus twice k psi is equal to C1, which is along alpha line, and p minus twice k psi is equal to Ct, which is along beta line. These set of equation, which is shown in equation number 14, is very well known equation, and it is known as Hanke's equation, and this is equivalent to equilibrium equation expressed along the slip lines. So for slip line, these two equations which is given in 14 is in fact equilibrium equation for rigid perfectly plastic material which undergo plane strain deformation. These equations are equations also indicate that the hydrostatic pressure varies along a slip line by an amount which is equal to twice k times the angle through which the slip line turns, and increase in hydrostatic pressure is obtained when an alpha line turns clockwise or a beta line turns anti-clockwise. So as shown here in equation figure number 4, where the velocity component in a perfectly deformed body is shown here. So this is what the alpha line from the x making psi, and the velocity is shown as v alpha, and along the beta line the velocity is shown as the v beta. So now we can use this figure to derive the velocity equations. So let us consider a pair of alpha and beta lines having the velocity component as explained v alpha and v beta, and if we resolve these two velocity component as shown in figure 4, and so we can write down that Vx is equal to V alpha cos psi minus V beta sin psi, and similarly Vy can be written as V alpha sin psi plus V beta cos psi. This is what is shown as equation number 15, and if we differentiate these two equations, so one can differentiate, and again it results the equation which is shown here in equation 16 after differentiation. So the first one which is differentiated, that is left hand side is deva Vx divided by deva x, and the right hand side, and similarly the second part is deva Vy by deva y, and what is that? These two is shown here in 16. If x and y directions are chosen to coincide with alpha and beta line as said earlier, that is when psi becomes 0, these equations, that is equation number 16, will result into deva Vx by deva x, and which is equal to deva V alpha minus deva x minus V beta deva psi by deva x, and second one deva Vy by deva y becomes equal to deva V beta by deva y plus V alpha deva psi by deva y. Since there can be no elongation or contraction along a slip line, which is the condition, therefore one can say that deva ux by deva x for psi when it is 0 is same equal to deva Vy by deva y, and that is both are equal to 0, and therefore this what gives the velocity equations. We would continue this lecture in subsequent 3-4 lectures, where once we establish the velocity equations, that is, we call it the Geringer's equation, Geringer's velocity equation, and then you can utilize the Encke's two equations and the velocity equations to solve many other problems with friction cases, with non-friction cases, with wedges, and with many other cases we would be considering. So, but still it will continue this chapter. So, I will thank you for your patience, and please go ahead, please see the other part that you would be considering. Thank you very much.